So this is Chapter 10, Section 2, number 51. We're going to look at this two different ways, an easier way and a harder way. I'm going to do the harder way first. So I'm going to just come straight at this, but the reason I came to this, I'm going to give you a quick explanation. To get ln of that, you integrate du over u, and you get ln of absolute u. Well, if I want this, that needs to be my u. So u will be 4 minus x squared to the 1/2 power, making du, using the chain rule, 1/2 of box, subtract 1 from the exponent, times the derivative of the box, which is minus 2x. The 2's cancel, so du is going to be x over 4 minus x squared square root dx. I think I'm missing something, but I'm not quite sure what it is. So to get that, I'd have to have the integral of u du. Oh, I know. No, I'm not sure what it is. So on u is going to be on the bottom, which is 4 minus x squared to the 1/2 power du. So if I put all this in here, I have x dx over square root of 4 minus x squared. Let me write that in. I'm missing a -4. I can't remember why, but it's no big deal right now. Oh, I remember where it comes from actually now. And this gets us x dx integral, and the two square roots on the bottom cancel each other out. So I end up with 4 minus x squared. Now, just to make it a little bit prettier, I factor 4 out of the bottom. I get 1 minus x squared over 4. And the last step, I get this. And one note, there's a negative I missed out here. See that negative? That should carry on through this whole thing. Negative, negative. So I'm just going to put it out in front. So I just know that's my target. If I get that, that's equivalent to that. So let me copy and paste this as a reference. I'm going to put that, well, I'll move it later. Let me erase everything else. So that's my target. So what I'm working for is this, but I start with something I know. So I know that the function 1 over 1 minus x, which is a geometric formula, is, I'm just going to do in summation notation only. That's x to the k, 0 to infinity. Just for time reasons. This is a very difficult problem, so I don't want to spend too much time on it. It's like something you will not actually see on an AP test. It's just so tedious and so much work. But the concepts are solid, so I want to still do this. So here's my first thought. I wish I had this, an x over 2 squared. So I replace x with x over 2 squared. Now I'm allowed to do that using one of the 5 properties of what I can do to a Taylor series. So this becomes 1 minus x over 2 squared. And in my series, I replace the x with x over 2 squared to the k, which gets me x squared over 4 to the k, which gets me x to the 2k over 4 to the k. Alright, so I'm getting closer to what I want. I want an x on top. So I have this. I still need the 4 and the negative 1 and the x on top. So next I'm going to multiply by x, which I'm allowed to. So I'm going to multiply everything by x. And now I have x over 1 minus x over 2 squared. And then I'm going to take this far right one here. If I bring in x, I'm going to have an extra one, so I have plus 1. So the integral of x to the 2k plus 1 over 4 to the k. Now what am I missing? I still need the negative and the 4. That's easy. So I put a negative, negative, and I'll put a 4 on the denominator. So I put a 1/4 here. And let me write this all out now. It's negative x, 4, 1 minus x over 2 squared, 1/4. Actually, I'm going to bring that 4 on the inside. And the negative I'm going to leave on the outside. So I have x to the 2k plus 1. On the bottom, I'm going to have k plus 1/4. Now that I have this, we can see that the integral of that is going to be that. So I can integrate both sides now with respect to x. Oh, on the right side, I accidentally, wow, that's sad, Yoshida. These are all summations, not integrals. Okay, we're going to integrate both sides. And the left side, because of all the work I did earlier, is this. So this becomes ln of the square root of 4 minus x squared. On the right side, so this is where you need practice understanding how to integrate and what things represent. So k is my variable, x is a constant. If you realize that and you integrate term by term, you add 1 to the exponent, so it's going to be 2k plus 1 over 4 to the k plus 1. That's a constant. And then I'm going to multiply or divide by 2k plus 1. So I add 1 to the exponent and I divide by that. That's how you integrate. So simplifying this, I'm going to get x to the 2k plus 2, 4 to the k plus 1 over 2k plus 2. Now some shenanigans. I want to reindex this. I want to start at 1 instead. Now, it's just going to make it a little prettier. And when I have actual terms, like term by term, I don't have it. I just did the summation, not term by term. You can see what number you have to start on to make it match up right. But what I'm going to do, instead of starting at 0, I'm going to start at 1. And here's where you have to process and think a bit. Here, if I put in 0, I start at 2, right? Well, now I'm going to start at 1 bigger. So if you think about it, if I'm starting at a bigger one, I replace this k with a k minus 1. So I'm starting at the same number. So it's going to be x to the 2k minus 1. And it's going to be 2 to the k minus 1. And what you're going to find is this simplifies nicely to this. It's going to be x to the 2k, and 4 is 2 squared to the k plus 1, and this is going to be to the 2k. I'm going to keep going. So this is x to the 2k, and this is going to be 2 to the 2k plus 2 over 2k. All right, that was a lot of craziness. Let me think here. Let me pause. Actually, I just realized something. I didn't replace this k with a k minus 1 with the other ones, leaving this now just being k and that being 2k. Okay, that's much better. So I have that final form. Now, since both of these are to the 2k power, I could do this. X over 2 to the 2k and 1 over 2k. Alright, now we got to back up a bit. So the original function, I'll do it in this pretty color. The geometric, it works when you have the absolute value of k is less than, okay, your r, your absolute value of your r, which is x, must be less than 1, not greater than 1. Yoshida. Your r, absolute value, must be less than 1 for a geometric. But we replaced x with x over 2 squared. So then this becomes x squared over 4, because that's x squared over 4. Multiply both sides by 4. We get absolute value. I'm going to move over. Absolute value of x squared is less than 4. Square root both sides. Absolute value of x is less than 2. So that is our convergence statement. This converges when absolute value of x is less than 2, or between -2 and 2. But we need to recheck our endpoints because we've done so many strange shenanigans. So let's test x equals -2 into this equation here and see what we get. We're going to get -2 over 2 to the 2k times 1 over 2k. Now, this is an even exponent. This is 1, so that's always positive. This is a geometric. You can pull that 2 out in front if you want. That's a geometric. This is a divergent geometric. Now you can try the other endpoint, x equals 2, and you will get this. 2 over 2 to the 2k, 1 over 2k, and quickly you see this is just 1. This also is a divergent geometric. So the interval of convergence is not going to include the endpoints. So that is my interval of convergence for that problem. Now, we're going to do this problem another way, which if I was smart, I would have noticed it, but I'm not that smart, and it would have made our life a lot easier. And I'm going to do a little cheating on this too. So, easy way. We're going to do some tricky algebra. Well, this is ln of 4 minus x squared to the 1/2 power. And we have a rule of logs. You can p in front of the log. So that becomes 1/2 ln of 4 minus x squared. Okay, to make this, we want a 1 there, and I'll explain why in a second, but we're going to factor out a 4. And this will be 1 minus x squared over 4, kind of similar to what we had before. Then we're going to break out more rules of logs. A log of two things being multiplied is the log of the first plus the log of the second. So we get that. Then we distribute the 1/2. We get that. Now, p-ing in front of the log, that moves up here, making it a square root, and the square root of 4 is 2. Now, here is more shortcut shenanigans. We previously, and the book previously explained this series. This series would be this. And it was found earlier, and I can't remember if we actually found it in the notes or anything. We may have. I think we did. But that is the series for ln of 1 minus x. So if we want this, we could replace x with x squared over 4. So ln of 1 minus x squared over 4, I just replace the x on this side with x squared over 4. And we're just going to do more and more algebra. So this will be x to the 2k over 4 to the k, and this k is still on the bottom. You can double check my algebra on that. And we're going to do more stuff. Let me double check my work here. I want to make sure I'm not messing up. Okay. All right, so I'm going to change that 4 on the bottom. That's 2 squared to the k. So we're going to get x to the 2k, 2 to the 2k, I mean 2 squared to the k is 2 to the 2k, and we still have a k left here. So we're getting somewhere, I think. So what we're going to do with all of this, we are going to place this in for the ln. So our final statement, ln of the square root of 4 minus x squared, is going to be, so we need this ln of 2 plus 1/2 of that. That's going to be ln of 2 plus 1/2 of negative summation x to the 2k over 2 to the 2k k and let me double check all this. That's going to be a minus on that. I think we're looking pretty good. I'm checking stuff here. So what we're going to do next, we're going to bring that 2 inside here. Well, we already have 2k 2's. One more is going to get us 2k plus 1. Is a minus. So we're going to get x to the 2k, 2 to the 2k plus 1, k. Now this looks different than our previous answer. I didn't spend the time, but I believe it's probably the same thing. except that ln of 2 out there is different, so it changes that. But I believe our answers are one and the same. So we should be good with that answer. Okay? You would do the same thing with the interval of convergence. You would have to test the endpoints. I'm not going to spend the time to do that, but that is problem number 51.